Okay, so we have found this velocity profile. A couple of things I should say. When we first wrote down this assumption, like the polynomial assumption, we assumed that Vx uh, is not changing with y. Sorry, is not changing with x. Vx is only a function of y. It's not changing with x. But you can say that, oh, you can actually like digest all the x-dependent terms into a0, a1, a2, a3, because I'm taking like a slice where the x is not changing. If I like get some x-dependent terms, that should be okay. If my boundary conditions give me an x-dependent term, I should take it into account. But you can see that it's like surprisingly the a0, a1, a2, and a3 are not x-dependent. So it looks like Vx is only a function of y, and particularly y over delta. And another thing I would like to mention here is that when you write Vx as a function of y in a form where you relate Vx over V infinity to the y over delta, it gives you some physical significance for the following reasons. First, the y is just going to be unitless this time if you divide by delta. The second thing is you can actually attribute the x dependency into the delta term because delta is a function of x. And Vx, if you divide by V infinity, also becomes dimensionless. The only x dependency is the x dependency in the delta. So Vx over V infinity, although it's depending on x, we don't have any other x-dependent parameters like in A0, A1, A2, A3, because every x dependency is in delta. Second thing is, please note that y is less than delta because I'm trying to study the boundary layer, meaning that y is going to be between 0 and delta. So y over delta is less than 1. And you know that if you actually take powers of a number which is less than 1, which is between 0 and 1, you get diminishing numbers, right? For example, try to take the square of 1 over 2. The square of 1 over 2 is 1 over 4, which is less than 1 over 2. And then if you take the cube of it, you're going to have 1 over 8, which is much, much smaller than 1 over 2. If you take 1 over 2 to the power 4, then it's going to get smaller and smaller, right? Well, actually, smaller and smaller than 1 even. So that tells you the following. Although I took up to the third power, you can actually expand this into like infinitely many terms, the power sum of this function, which is going to be something like a Taylor series expansion. And you're going to see that up to a certain point, the powers are going to make the term much, much, much smaller than 1, so that you can actually neglect those terms. Okay, so that's basically one of the reasons that we divide y by delta when we actually do the power expansion, power series expansion, so that our terms can be approximated up to some power, to some polynomial, and beyond which we can neglect because they're going to be increasingly small. Okay, so those are the important things. Another thing here, although I made no assumption about whether the A0s, A1, A2, A3 depend on X, at the end, the boundary conditions gave me this equation, which tells me that these terms do not change with X. Okay. So the only X dependency is here in delta X. And this tells us also another thing. You can think about, instead of Vx depending on Y, you can think about Vx over V infinity depending on Y over delta X. And you can actually think about the following plot. Imagine that you have this velocity profile here, okay? Then not changing anymore. And then another velocity profile. And this equation tells you that this thing is just the zoomed out version of this thing. Because if you actually zoom in and zoom out, this thing, the velocity, changes from 0 to v infinity. So basically this changes from 0 to 1. Similarly, again, from here to here, this v or vx over v infinity changes from 0 to 1. Basically, they are the same things. They are the same functional form. Similarly, this is your y-axis. Although the y is 0 here and delta here, and delta 1 you can call it, and the y is 0 here and delta 2 here, the y over delta is the same in both cases, y over delta versus v over v infinity. We have the same function, so this is at, for example, y is equal to 1, you get 3 over 2, or so you get at 1, you get 1. So the velocity profile is always this. The reason why they look different, the one on the right is just the zoom in version of the one on the left. Okay, so this is called similarity stretching. Sometimes people start with this assumption and find it, but with this integral analysis, integral method, it turns out to be that up to certain approximation, up to the powers of 3, the similarity stretching assumption is correct, because we find a formula which relates the vx over v infinity to y over delta x, with the terms not changing with x or y. Okay. The next thing we do, we're going to actually plug it in our formula, right? We found that vx over v infinity is equal to 3 over 2 y over delta minus 1/2 y over delta cubed. And let's plug in this in. The von Karman integral formula. Get v infinity squared d over dx integral from 0 to delta let me write the equation first before we plug in vx over v infinity. 1 minus vx over v infinity dy is equal to nu dvx over dy at y is equal to 0. Why did I use 1 minus? Because let's have a look at this equation. You have this, okay, here. You have this minus term here. I made it positive, and I actually changed the sign of this as well. Okay, so this become 1 minus this instead of that minus 1. Okay. Let's plug this in. Let's plug this thing in here and here. We get v infinity squared d over dx integral 0 to delta in parentheses over 2 y over delta minus 1/2 y over delta cubed times 1 minus 3 over 2 y over delta plus 1/2 y over delta cubed dy is equal to nu dvx over dy, y is equal to 0. Okay, and let's simplify this to make the steps simpler. Let y over delta be eta, and dy is going to be equal to delta times d eta. Okay, and then since y goes from 0 to delta, the eta is going to go from 0 to 1. So the integral becomes let's just focus on this integral. From 0 to 1, delta 3 over 2 eta minus 1/2 eta cubed right? 1 minus 3 over 2 eta plus 1/2 eta cubed d eta is equal to delta does not depend on y or eta, so you can take it out, right? And then you have in parentheses 3 over 2 eta minus 9 over 4 eta squared plus 3 over 4 eta to the power 4 minus 1/2 eta cube plus 3 over 4 eta to 4 minus 1/4 eta to power 6 d eta. Let's combine the similar terms. So it's going to be 3 over 2 eta. I only have 1 eta, right? This one. The eta squares, I have this one only, minus 9 over 4 eta squared. Eta to power 3, I have only this one, minus 1/2 eta to power 3. Eta to power 4, I have 2 of them, so I have 3 over 2 eta to power 2 and 4. And eta to 6, I only have 1. 6 d eta. Okay. So what do I have here? Let's see. Three eta squared, right? Minus oh no, I need to divide by 2. 3 over 4 eta squared minus 9 over 12, which is 3 over 4 eta cubed minus 1 over 4, 1 over 8, I'm sorry, eta to 4 plus 3 over 5 times 2, 10 eta to 5 minus 1 over 28, eta 2, 7, from 0 to 1. If you plug in 1, you just get rid of all the etas, but have the prefactors. If you have 0, all the terms vanish. So you have delta 3 over 4 minus 3 over 4 minus 1/8 plus 3 over 10 minus 1 over 28, right? And these cancel. You get how many deltas? If you do the calculation, you will find something like 0.139, okay, delta. That's the integral part. So what you get is basically v infinity squared times the d over dx, the integral, which was 0.139 delta x. You got a really simple answer, right? On the right-hand side, you have mu del Vx over del y. Y is equal to 0. Okay. And you calculate the del Vx over del y. Since Vx over V infinity, sorry, is equal to minus 3 over 2 y over delta plus, I guess it was the other way around, right? Half y over delta cube. Okay, so del Vx over del y becomes equal to V infinity times 3 over 2 delta minus 3 over 2 delta cubed y squared. And this evaluated that y is equal to 0. You get V infinity times 3 over 2 delta. Okay. There you go. Okay, so that's the right-hand side. What the right-hand side becomes. And you get the following. V infinity squared d over dx delta times 0.139, okay, is equal to 3 mu V infinity over 2 delta. Okay, and let's collect all the delta terms on one side. Delta d delta over dx is equal to, well, actually, let's make it 2 delta. Okay, 2 delta. And then you get 3 nu divided by 0.139 V infinity. Okay. And this term is nothing but the derivative of the square of the delta, d over dx, delta squared, is equal to 3 nu over 0.139 V infinity. So delta squared becomes equal to 3 nu over 0.139 V infinity times x plus some constant C1, okay, after integration. And we should use some boundary condition. We know that as x goes to 0, what happens to delta? Any idea? This is x is equal to 0. This is x is equal to L. This is your profile. This is your delta at any x. What happens to delta when x goes to 0?
Delta equals 0?
Exactly. It goes to 0. Right? So what is C? Then C1 is equal to 0. So that means delta squared is equal to 3 nu x over 0.139 V infinity. We got a pretty neat equation, huh? Then you can do the following. Let's divide by x squared both sides. Now delta over x squared comes out to be equal to 3 nu over 0.139 V infinity times x, right? There is a dimensionless number here that you can actually realize. Nu over V infinity times x. We can define it as the Reynolds number up to the point x. So remember, we had defined the Reynolds number L as, so that's basically, it's 1 over, I'm sorry, 1 over Reynolds number. We had defined, remember, it's the L or V infinity L over nu, right? So for L is equal to x, or instead of L, if you use x, the Reynolds number x can be defined as V infinity x over nu. Okay, so that's a dimensionless number, but it's changing with x, so we made a new definition. So from here, our equation gives us delta over x is equal to square root of 3 over 0.139 Reynolds number x to the power negative 1 over 2. Negative because it's in the denominator, 1 over 2 because we are taking the square root of it. And from here, if you take the square root of that constant term, you get something like 4.64 Reynolds number x to the power 1 second. Is this the correct behavior? The expected, let's say, expected equation or behavior? I mean, am I expecting the thickness of the boundary layer decreasing with the Reynolds number inversely proportional to the square root of the Reynolds number? Is that my expectation from previous classes? Let me show you. Have a look at this. Does this ring a bell? Yes, right? We know that the Reynolds number should scale with the inverse square of the boundary layer thickness, and that's exactly what I'm getting. But in this form, like previously, I didn't know what that constant or the proportionality constant was, but now, oops, I actually solved this equation approximately to get an idea about how the Reynolds number and the boundary layer thickness is changing with respect to each other. Okay. Okay. What about the shear stress? Tau wall is equal to 3 times mu v infinity over 2 delta, correct? Because have a look at this. We got this, where is that? Right-hand side. Yeah, here. This is the velocity gradient, and if you multiply it with the mu viscosity, then you get the shear stress, right? So this is the shear stress at the wall, and let's define it as the absolute value of it. Okay. Let's take a note here. Since tau wall is equal to mu del Vx over del y at y is equal to 0 from the velocity profile we find. Now, how about a quantity called the skin friction coefficient, CF, which is skin friction coefficient. That's equal to tau wall divided by 1/2 rho v infinity squared. If you remember from your fluid mechanics course, it's the friction, sorry, it's the shear stress normalized by the kinetic energy of the, or the kinetic energy density of the fluid. It's equal to, your numerator is 3 mu v infinity divided by 2 delta, and the denominator can be written as 2 over rho times v infinity squared, right? From here, CF is equal to, cancel the 2's, cancel one of the v infinities, 3 mu over rho delta v infinity. So it's a function of x, right? Because the delta is also a function of x. You can write it actually in terms of Reynolds number if you like, if you actually can make some simplifications. And as such, 3 mu over rho v infinity okay. Instead of delta, or 1 over delta, we had found that, let's see here. You can write the delta as, you can basically use this one. X times 4.64. Reynolds number to the power 1/2, negative 1/2. Or we can actually write it here. The Reynolds number is V infinity x over mu. Yep. Okay. That's equal to 3 over 4.64. Take everything inside the parentheses. So you get mu squared over rho squared V infinity squared. So I'm actually rearranging these terms. I'm taking it inside the square root. Okay. Times I have x squared in here. And what do I have? V infinity x over mu. I guess that's all, right? So from here, CF comes out to be 0.646. Let's do the simplifications. Of the x's go, these go, and mu is nothing but mu over rho, right? So one of the rho's go, one of the mu's go, and you get mu over rho V infinity x. So it's basically one over Reynolds number. So CF came out to be 0.646 Reynolds number x to the power negative 1/2. Excellent. So we have found a formula for the friction coefficient as well.